there's your thought for the day. Anybody ever tried to pick up a turtle?
Yes. No.
All right. So 3-3 is the Pythagorean theorem in right triangles. Our objectives are to find the length of the sides in a right triangle using the Pythagorean theorem and find the lengths of the sides in special right triangles. Theorem 3.8 says that the Pythagorean theorem is the sum of the squares of the lengths of the legs of the legs of a right triangle is equal to the square of the length of the hypotenuse. A squared plus B squared equals C squared. Now, I'm going to introduce, there's some things called Pythagorean triples. They're combinations of numbers that always make the Pythagorean theorem work. Some examples are 3, 4, and 5. 3 squared is 9, 4 squared is 16. 9 plus 16 is equal to 25. Another example is 5, 12, 13. 25 plus 144 equals 169. All right. So those are Pythagorean. Those are the most common Pythagorean triples we use in there. There's a few others, but the numbers get kind of big. Yes, Shatish, you have. Oh, you just.
Yeah, I have a question.
What's your question?
I do have a question.
Uh-huh.
Okay, wait. So how do you know which ones are which one's which one? Is it like this one's A, B, and C, or?
Right. The two smaller numbers are always going to be A and B. C is always the larger number. The hypotenuse
Does it matter where it goes? Where A and B go?
No. Okay. Doesn't matter what order A and B is in. All right. So I would memorize these 3, 4, 5, and 5, 12, 13. I don't think you'll have to use any of the other Pythagorean triples. There's one 15, 17, 8, something with. There's another one that's not too big of numbers, but you can figure that out as you work through the problems if you need to use that one. But the Pythagorean multiples is where these also come into play. The Pythagorean multiple is a multiple of the Pythagorean triple, and they also work. So like if I have A, B, and C, and I take 3 times A, 3 times B, and 3 times C, if I did the Pythagorean theorem on those numbers, they would work as well. For example, if we take the combination of 3, 4, 5, and we multiply it by 3, we have 9, 12, 15. Okay, so let's do 9 squared plus 12 squared equals, question mark, because we don't know for sure, 15 squared. And if we multiply those out, we get 81 plus 144 should be 225, which is the square of 15. And it is. It's 225. So, if you can recognize that you have a Pythagorean multiple of 3, 4, 5, or 5, 12, 13, or any of the other Pythagorean multiples, triples, then you don't have to show the Pythagorean theorem. You don't have to show your work. For example, if I had a triangle, let's say we were working with the 3, 4, 5, and it's multiplied by 2. So if I had a triangle, right triangle, its legs were 6 and 8, then I automatically know that the hypotenuse would be what?
10.
10. I multiplied everything by 2. You don't have to show your work. You can just say it's 10 because you recognize. I think that's mental math. You could recognize that those are multiples of 2 of 3, 4, 5. Does everybody get the idea? All right. Here's an example. We have to find x. So we write a squared plus b squared equals c squared. And we do 4 squared plus 5 squared equals x squared. So that's going to be 16 plus 25 equals x squared. So x squared equals 41. So then x equals approximately 6.4 inches.
And like quizzes and tests, when we have to use this, do we just leave it like the square root of 41, or do we actually try to solve it?
Good question. I will specify what I want you to do.
Okay.
All right, let's do this one. This involves some algebra here. We've got a squared plus b squared equals c squared. Remember, it only works on right triangles, so you have to see the right angle. So we have x squared plus x plus 1 squared equals x plus 2 squared. And we multiply everything out, so we would have x squared plus 2x plus 1 equals x squared plus 4x plus 4. And so then we have x squared minus 2x minus 3 equals 0. So then we have, in fact, we factor that, and that factors into what? Does that factor into?
Negative 2 and 1. Wait, no.
Yeah, so it would be x minus 3 times x plus 1 equals 0. I have to think of the multiples of negative 3 that would, when I add them, they would add to be negative 2. That's how you...
Yeah, I was trying to think, but then I got a little bit confused.
Yeah, well, this is a refresher on that. You'll do some problems like that that'll give you some practice doing that. So we've got, we solve for x. X equals, x can't be a negative number, so it's just going to be x equals 3 centimeters. It's not x equals negative 1, right?
Wait, so if we plug it in, it shouldn't be like true. Wait, so that's 3, 4, and 5, and that's our Pythagorean triple 3, 4, 5. So
that's right. It works. Yeah, you can check it by plugging it back in, seeing if it's satisfies the Pythagorean theorem. All right. So we have to find the area of a square that has a diagonal 10 inches long. So to find the area of the square, we need to find S. How could we do it? Shatiz.
2s squared has to equal 10 squared.
Right, we could say s squared plus s squared equals 10 squared, so that's going to be 2s squared equals 10, so s squared equals 50. Take the square root of 50. But we don't have to do that, because what do we know that s squared is also equal to what? The area of the square, right? So we don't have to do the square root. We can just, once I find s squared, that's what I needed to know. S squared equals the area, so the area is going to equal 50 inches squared. All right, any questions there? Okay. Test for right triangles. If a squared plus b squared does not equal c squared, then ABC is not a right triangle. So if we're given numbers, like 11, 15, and 19, we're going to take 11 squared plus 15 squared, and we're going to see if that's equal to. If we're not sure, don't put equals, because we don't know if it's a true statement yet. So put a question mark above your equal sign. That shows that we're trying to show if that's true. Equals 19 squared, and then we square them out, so it would be 121 plus 225. Is that equal to 361? And we add those together, it's 346. Does not equal to 361, so that is not a right triangle. All right, let's do the other example. Now you have to be careful. Like we said before, when you do the Pythagorean theorem, your a and b are always a smaller number. So they switched up the order on these. The larger number is the second number they give you, but you still want to make sure it's on the right side of your equality. So we would have 7 squared plus 16.8 squared equals 18.2 squared. And we multiply that out, so we get 49 plus 282.24 is equal to, they should have question marks above our equal sign, equals to 331.24. I add those up, and we get 331.24 is equal to 331.24. So it is a right triangle. All right, any questions? Special right, okay, then the Pythagorean triples, we talked about that. Something it's kind of useful to know for the Pythagorean multiples. All right, for multiples, I can come up with multiples by, if I have two numbers. So I have, you pick any two numbers, like u. If so I take, we'll call one u, we'll call u 2, and v 3. then if I want to come up with a Pythagorean multiple, A is going to equal to 2uv, B equals u squared minus v squared, and C equals u squared plus v squared. So then I plug in my values. So A would equal to 2 times 3, which is equal to 12. B is equal to 3 squared minus 2 squared, which is equal to 5. And C is equal to 3 squared plus 2 squared, which is equal to 13. And so we have the Pythagorean multiple of 5, 12, 13. Now I could pick other numbers. I could pick 3 and 5. If I plug those in to those combinations, it would spit out a Pythagorean triple or a Pythagorean multiple. Yes.
Wait, so you have to so you can choose 2 numbers and then like you can use a Pythagorean theorem to find the third number?
No, we're not using Pythagorean theorem. We don't know what the third number is, but I could figure it. I just pick 2 numbers. They aren't going to be in the Pythagorean theorem. If I just wanted to come up with a Pythagorean multiple, I could pick any 2 numbers. If I pick 3 and 5, I plug those in for u and v, it's going to give me an a, b, and c that's a Pythagorean multiple.
Oh.
All right? So special right triangles. Let's take this triangle, and we'll take an equilateral triangle. Right? We know all the angles in an equilateral triangle are the same. It's equiangular as well. It's a regular triangle. We'll say the side length is 2a. If I drop an altitude, then half of 2a is a, and our height is, we'll call the height h. So if I do the Pythagorean theorem on this, I should have the hypotenuse is 2a, so we'd have 2a squared is equal to, we're doing half the original triangle, so we'd have a squared plus h squared. And I multiply everything out, so we'd have 4a squared equals a squared plus h squared. So h squared equals 3a squared. So h is going to equal to the square root of 3 times a. So, and that gives us, that ratio is always going to work in this situation. What would this angle be in the bottom left? What would that angle be? How many degrees would it be? It's equilateral triangle. All the angles are the same, Shatice.
60.
It would be 60. And then since I dropped the altitude, since it's equilateral, that divided back exactly in half, so this is 30. So this is what we've come up with the ratios of these sides. It's called a 30-60 right triangle. In a 30-60 right triangle, the hypotenuse is radical 3 times, or no, sorry, the hypotenuse is twice the length of the leg opposite the 30-degree angle, so the short side, and the length of the leg opposite the 60-degree angle is radical 3 times the leg opposite the 30-degree angle. So with a 30, 60, 90, you always want to do what I call the map. You map out the side ratios. The side across from the 30 is always going to be A. Don't use x, use a, because when you take pre-calculus, that's the variable they use. So I want you to get used to using a. So the side across from the 30 degrees is a. The side across from the hypotenuse is 2a. And the side across from the 60-degree angle is a radical 3. The sides will always be in this ratio in a 30, 60, 90. So, because they all have the variable a in them, if I know one of the side lengths in a 30, 60, 90 triangle, I can find the other two using these ratios. Let's do an example. Find the missing side lengths of the 30, 60 right triangle. So we have across from the 30 is a, across from the 60 is a radical 3, and the hypotenuse is equal to 2a. So I take the known side, so we have 2a equals 4. I'm going to solve for a. A equals 2. So this side would equal 2. And then a radical 3 is going to be 2 times radical 3. So my other side is equal to 2 radical 3. Any questions? Yes, Shatis.
In any test, will we have to find the exact value of it?
No, we'll leave it in radical form.
Okay.
Unless I say to round. Alright. So when I grade these problems, I will always give you a point for drawing the map. In other words, labeling the sides a, 2a, and a radical 3. I want you to do that, so then it just becomes a matter of seeing which one I know and solving a algebraic equation to find the value of a. Let's do another example. This time, so the side across from the 30 is a, the side across from the 60 is equal to a radical 3, and the side across from the 90 is 2a. The side across from the 60 is always, it is the one we know. It's 5. So we're going to say a radical 3 equals 5. So that means a equals 5 over radical 3. And 2a would equal to 5 times 2, 10 over radical 3. Everybody get the idea? Any questions? No questions. Now we're going to do a 45-45 right triangle. So to think about the ratio for that one, if I take a square and I draw a square side length S and I draw a diagonal, okay, we'll call the hypotenuse C. Then we would have S, S, and C, and so we would have side squared plus side squared equals C squared. So 2S squared equals C squared. So C equals the square root of 2 times S. So the hypotenuse is radical 2 times longer than the side in a 45-45 right triangle. In a 45-45 right triangle, the length of the hypotenuse is radical 2 times the length of the leg. So here's my right triangle. This is a 45-45 right triangle. And so we would have, this would be S radical 2. That's our map for a 45-45 right triangle. Let's do an example. If I had a right triangle and the hypotenuse was 7, this is a 45-45 right triangle. I would label the sides S, and well, I said to use A. We should use A. Let's use A. So we'll say the sides are A, and then the side across from the hypotenuse is A radical 2. Right? So I come over here, I say A radical 2 equals 7. So A equals 7 divided by radical 2. The whole key is labeling the sides correctly. The algebra is not that difficult. It's usually a simple equation. You usually have to divide or multiply. Let's look at this example. I have to find the area of this parallelogram. Yeah?
Will the hypotenuse always, in a 45-45 right triangle, will the hypotenuse always be the opposite of the 90-degree angle?
Yes, the hypotenuse is always opposite the 90-degree angle. How can I find the area of this parallelogram? Yes?
Well, first we need the height.
Okay.
Which, if you use this right triangle, which pretty much I think it happens to be a 45-45, 90 right triangle, we could use the layout here. Considering this would have been that is the side radical 2 and those are sides. We could take that 42 would have to be 42 would have to be S.
Okay, yeah, so you're going to use a 45-45 triangle. So we would have, so this other angle we know is 45 because it's 90 and 45, so that's a 45-45 right triangle. So the hypotenuse is 42. 42 is equal to, and the if we label our sides, this is H, we could call this H, this would be H radical 2. So 42 equals H radical 2. So then we solve for H. H equals 42 over radical 2. So my area, now that I know the height, 42 over radical 2, area equals base times height. So it's going to equal to 86 times 42 over radical 2, which is equal to approximately 2,554 inches squared. Any questions? No questions.